Hi there, welcome to Study Heroes once again. This is part 2. We'll be going through questions that will help us understand the applications of Newton's laws. In this one, I'll be going through the March 2025 paper. This is the Limpopo paper. So, March 2025 test, question 2. Question 2 should cover some of the Newton's laws application questions. So it says here, a boy on a skateboard is pulled by a horizontal force F to the left, as shown in the sketch below. The combined mass of the boy and the skateboard is 60 kilograms. A total frictional force is 70 newtons opposing the motion. The boy and skateboard accelerate at 1.5 meters per second squared to the left. Ignore the rotational effects of the wheels. And then we get to 2.1 that says draw a labeled free body diagram showing all the forces acting on the boy and the skateboard together. So 2.1, they ask us to draw a free body diagram. Free body diagram meaning excluding the body, so I'm going to use a dot to indicate the body, and I'm going to start off. Let's have the image of the skateboard here so that we can remember what it is we are drawing. So I'm going to start off with weight. I like to start off with weight because most objects have a mass and therefore they will have weight. And because this is moving to the left, not up and down, up or down, that means it will have an opposing equal force called the normal force. And there's an applied force indicated over there. So we have applied force moving it to the left and frictional force opposing the motion. So you don't have to draw these to scale because no values are used. We have weight, normal force, applied force, and friction force. But as you can see, we indicated the frictional force just less than the applied force because there is motion, and it's just to show that this will be more than this if the object is moving in that direction, the left direction. So that's 2.1. In 2.2, they ask us calculate the magnitude of the force F. And the force F, if we go back to the image, is the applied force there. So what is the magnitude of F? Let's go back to that free body diagram we just drew. Like I said in the previous video, if you've watched it, the free body diagram will help us analyze all the forces. So for 2.2, they want to know what is the value of F. The value. Now, if you go back to the information, you'll realize that certain things were given to us, and they'll also help us in finding the value of F. So, the mass of the boy and the skateboard is 60 kilograms. And the frictional force is 70 newtons. And the acceleration to the left is 1.5 meters per second squared. Let's just write this down quick so we can have it nearby. We had a mass of 60 kilograms. we had a frictional force of 70 newtons. Now remember, the frictional force was to the right. And we had a net acceleration of 1.5 meters per second squared. And this was to the left because the boy and the skateboard is moving to the left. So if we check this line where there's movement, so that's our x-axis. First we have to state which direction we are going to analyze this question. So it's up to you to choose whether you want to analyze left as positive or right as positive. I'm going to choose left to be positive. Why? Because it's in the direction of movement. But even if we said right as positive, we just have to indicate that this would be positive and that would be negative. But in this case, I'm saying left is positive, therefore that is positive, this is negative. It's important to stick to whatever assumption you make so that your answers are right at the end of the day. So with left as positive, we have, back to our free body diagram to understand, we have our applied force in that direction. So that's adding our applied force, subtracting, because it's towards the right, our frictional force. So we're subtracting our frictional force, and this will equal to our F net. Now if you don't know by now, F net, your net force, is equal to the mass of the object and the acceleration of the object. So the acceleration was given to us, our F was given to us as 70 newtons. Therefore, since we have this value and don't have this value, we can get F. So if we make F the subject of the formula, we'll have F is equal to F net. We are taking F, our frictional force, to the other side. We'll add it, so plus F. So we have applied force equal to F net, which is MA. So MA plus F, which is 70 newtons. 70 newtons. Let's keep going with this. Therefore, that means F is equal to mass, which is 60 kgs, multiplied by 1.5, which was acceleration, plus 70. 60 times 1.5 is 90. Adding that 70, we get 160 newtons. So our applied force for 2.2 is 160 newtons. And it's already indicated on the diagram that F is to the left. So we are calculating magnitude. If they didn't ask us magnitude specifically, we'd have to write the magnitude plus the direction. We'll have to say 160 newtons to the left. But they ask for magnitude, so 160 newtons. Let's go to 2.3. In 2.3, they tell us that the force F is increased several times and the acceleration is measured for each value of F, while all the other forces remain constant. Draw a sketch graph for the system showing the relationship between the acceleration and F from the moment F acts on the system. Okay, let's start off here. Let's start off by drawing a axis. Since every graph has to have an X and Y axis. So what are we changing here? We're changing the force and we are observing the acceleration. So that means our independent variable is going to be force in newtons, increasing in that direction, and on the y-axis we'll have acceleration. I'm just going to state A. The unit of measure will be meters per second squared. In that direction, we know that as soon as 160 newtons was applied, so in this point here, we had 160 newtons, and that gave us an acceleration of 1.5 meters per second squared. And if you know the formula F equals ma, you would know that acceleration and force are directly proportional to each other, which means when force increases, acceleration increases, and therefore we'll have a linear relationship between force and acceleration. And that will be our graph for question 2.3, indicating that when we increase our force, our acceleration will increase, and that's the relationship between force and acceleration. But this is all we needed to draw to get full marks for that question. They just wanted to see a linear increasing directly proportional relationship. Let's go to the next question. 2.4. 2.4 states that when force F is removed, the boy and the skateboard continue to move to the left for a short distance. The skateboard then hits a stone and stops. Explain what happens to the boy. So obviously when the force is removed, let's think about this. This boy and skateboard is being pulled in that direction. They're moving, right? And then the force is removed. When the force is removed, they're still in movement, right? So picture this gun, the force is removed. The boy and skateboard are still moving in that direction. But it hits a stone. The skateboard specifically hits a stone and stops. But the boy didn't hit the stone, just the skateboard. Obviously the boy is gonna fall off the skateboard and keep going. And that's what happens to the boy. He keeps moving. But the skateboard has stopped. Although the skateboard has stopped, the boy keeps moving. So in 2.5, they say name and state the physics law which is applied in question 2.4. Now the physics law that is applied in 2.4 is Newton's first law. Newton's first law states that a body will remain at rest or at motion unless a net zero force is acted on it. Remember, the force was removed from the boy and the skateboard, so it kept moving, it remained in motion. But a opposing force stopped the skateboard, but the boy didn't experience an opposing force, and therefore the boy continued to move because no other acting forces were applied on the boy. So the answer to 2.5, if we go check Newton's laws from the exam guidelines, which states that a body will remain in its state of rest or in motion at constant velocity unless a non-zero resultant force acts on it. So I'm going to leave this here so that you can see what Newton's first law is if you did not know Newton's first law. And since we now know that Newton's first, second, and third law of motions will be asked in these questions, might as well state Newton's second law and remember it. And I'll show you Newton's third law after this. But Newton's second law also states that when a net force acts on an object, the object will accelerate in the direction of the force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. Newton's third law states that when an object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. So as you can see, or as you have seen, they could ask you to state any of these laws, and you need to understand them. So take your time to understand these laws and also memorize them so that when you are asked to produce them, you have them in memory. The next question we'll be looking at is the physical science paper 1 from 2018. It's the November NSC paper. So question 2 once again. In question 2, they have a block of mass 8 kg is placed on a rough horizontal surface, and the 8 kg block, which is connected to a 2 kg block by means of a light inextensible string passing over a light frictionless pulley, starts sliding from point A as shown below. So this block moves that way and is connected to that. 2.1 says state Newton's second law in words. So we covered the laws. Just to reiterate Newton's second law. Newton's second law of motion states that when a net force acts on an object, the object will accelerate in the direction of the force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. Best way to remember this is to recall the formula F equals ma and make the acceleration the subject of the formula. So you'll have force directly proportional and mass inversely proportional. So let's go through it again. And when net force acts on an object, so F net acts on an object, the object will accelerate in the direction of the force. The acceleration is directly proportional to the force and inversely proportional to the mass of the object. Let's go back to the question. Let's go to 2.2, which states draw a labeled free body diagram for the 8 kg block. Let's look at the 8 kg block. So what forces are acting on the 8 kg block? Let's explore that. 2.2. We have the 8 kg block. Remember, this is a free body diagram, so we're going to represent it by a dot. And I like to start with weight. So downwards we have weight. From the center of mass, pulling it down, pushing it down. And then we have the tension. It's 15 degrees connected to the rope. And there's always a normal force acting from the surface that's perpendicular to the surface. And they did mention that there is friction. They mentioned that there's a rough horizontal surface. So there's friction that is in line with the surface. So we have friction, we have our normal force, we have our tension, and we have weight. 2.3 states that when the 8 kg block reaches point B, the angle between the string and the horizontal is 15 degrees, and the acceleration of the system is 1.32 meters per second squared. In 2.3.1, they say give us a reason why the system is not in equilibrium. So if a system is in equilibrium, that means that your F net, which is your sum of forces, will equal 0, which means that there is no acceleration. So I'm just going to put no acceleration, A equals 0, that's why F net equals 0, which means that your object is either moving in a constant velocity or not moving at all. So, okay, in 2.3 here, they stated that the 8 kg block, point B, has an acceleration of 1.32 meters per second. Now, as soon as they state that, you know it's not in equilibrium anymore because there's an acceleration for the net force or sum of forces. So in 2.3.2, they say use the 2 kg mass to calculate the tension in the string. So 2.3.2, we have a mass. If you think about it, it's subjected to only two forces, which is weight going downwards, and tension. And we've been given an acceleration for the system. So as you can see, our forces are only acting on the y-axis. So our F net is going to equal the sum of forces along y. It's going to equal to mass times acceleration. Just as a reminder, what are we looking for here? We're looking for T, tension. So this seems like it will be a simple one, because we know the sum of forces along y is just tension and weight. Right? So if we take up as positive, remember that's generic, you can take up or down. We have our acceleration going downwards, because if this block is moving that direction, accelerating in that direction, and it's connected to the string, meaning this mass over here is pulling this mass in that direction, that means it has to be pulling it downwards for it to move that way. So our acceleration is downwards for the 2 kg mass, and gravity is also acting downwards. We need these two variables because our sum of forces on y is equal to mass times acceleration. So our mass is that 2 kg. Our acceleration is that 1.32, is it 32? Let's see, 32, yes. 1.32 meters per second square, and our g is 9.8 meters per second square. So again, sum of forces along y equaling to ma. We set our sum of forces over here along y is equal to tension and weight. So our tension plus our weight, which is equal to m times g. Remember, W equals mg. And that should equal to ma. M is 2 kg. And our acceleration is 1.32, but in the downward direction. And we said up is positive. So that'll be negative 1.32. Our tension is what we're looking for. Our weight is equal to mg. Our mass is 2 kg. And gravity acting downwards, so we put the negative there, is 9.8 meters per second squared. If we multiply these two, we'll get negative 2.64. If we multiply these two, we'll get, let's see, 18, 19, so we'll get minus 19.6. So our t, if we bring this to that side, we'll be adding it. So let's just do it in full. 2.64 plus 19.6. We get 16.96 newtons. So that's our value for tension, 16.96. If we go to the next question, 2.3.3, says calculate the kinetic frictional force between the 8 kg block and the horizontal surface. So let's check that picture. We got an 8 kg block, we got a surface, and there's a friction acting on it. We have indicated it here on the free body diagram. Maybe we can write 2.3.3 right next to it. 2.3.3, we are looking for F. And we know the block is 8 kilograms. We now know what tension is. So remember that when you have a angled vector like this, you can split it into two components. The x component and the y component. So let's call this ty and call this tx. right? So now we can analyze the sum of forces along the x direction, since the block is moving in that direction and not in this direction. And then we realize that the sum of forces, sum of forces of x equals mn is just friction plus the x component of the tension. Our mass is 8 kilograms. Our acceleration was stated as 1.32 meters per second to the right. So now I have to state what is positive, what's negative. I'm going to take right as positive. So right is positive. You have to state what you're working with. So if I take right as positive, that means our F and our T component of X. Now our T component of X see, this is our angle of inclination. Our T component of X is adjacent to the angle. It's not opposite, it's adjacent. So if it was opposite, we'd be using sine. But because it's adjacent, we're using cos. So our T component, our X component of T is equal to T cos our angle. And our angle in this question was given to us as 15 degrees. So 15 degrees. So coming back to this, the sum of forces along X is F minus, it's minus F. Why minus F? Because F is pointing towards the left. And we picked right as positive. So since it's pointing towards the left, our F is moving towards the negative direction. So it's negative F. Then we add the T component of X, which is pointing towards the right. So plus T, what is T again? T was calculated as 16.96. Or maybe I should just substitute it in. So the T component of X is T cos theta. And that will equal to mass times acceleration. So now we have F, negative F, and we have T, 16.96 cos 15 degrees times mass 8 kgs times acceleration 1.32. It's to the right, so we chose right as positive, so that remains positive. And then Let me grab a calculator. So if we multiply these two, we get negative f and 16.88. Sorry, 382. Then if we multiply these two, we get 10.56. Then if we take this to that side by subtracting 16.382 on both sides, we get minus f equal to 10.56 minus 16.382. And that is minus, let's see, negative 5.822. To make this positive, we multiply by negative 1 on both sides, and we get f equals 5.822 newtons. So that's our answer for F. Let's go to 2.4, which says, as the block moves from A to B, the kinetic frictional force between the 8 kg block and the horizontal surface is not constant. Give a reason for the statement. So now the kinetic frictional force changes as it moves from B to C. As you can see, if it moves closer to C, the angle here should change because it's moving closer to the pulley, which is higher than the block. It's not on the same line, so the angle should be changing. And that should affect what X component and what Y component of the tension is acting on the block. So the answer to 2.4 is that the angle will change, and therefore the tension changes as it moves towards C. Then they state that the horizontal surface on which the 8 kg block is moving is replaced by another horizontal surface made by a different material, with a kinetic frictional force calculated in 2.3.3 above. Change, choose yes or no. Give a reason for the answer. The answer is yes, because the surface based on the material should change the frictional force. So like we said earlier, if the surface is smooth, the frictional force decreases, and if the surface is rough, the frictional force increases. And that is caused by the type of material that is used on the surface. Alright, and that's it from the NSC November 2018 paper.